So crankcase strategy. The engine's got to breathe. If you don't let this engine breathe, you know, the blow by from the cylinders, just the pistons going, you know, down in towards the crankcase, all that pressure being created right there. If you don't let it breathe, then you'll blow out a rear main, a oil pan gasket, a cylinder head gasket, a timing cover gasket, or timing cover seal. So to prevent that, we are going to capture that crankcase ventilation, and we're going to try to separate all of the liquid from the gas. Oil vapor, what the engine wants to breathe, is both liquid and gas. The liquid, we want to separate and let it drip back down into the crankcase. The crankcase emission gas, we can burn it. So we'll put it back into the inlet side of the turbo, and we can burn it. So crankcase strategy, a long time ago, we used to downspout. We just let it go to the side of the engine. And if I ever lifted a vehicle up and I didn't see oil all underneath the undercarriage of the engine, I had known that the engine was low on oil. Nowadays, though, we capture all that oil vapor, and we have filters that will, especially on this Cummins right here, we call it a CCV filter. It sits right near the oil fill cap. That filter right there's got a couple sensors that we can test the pressure on the inlet and the outlet side of that filter. If the sensors read the same, it must not have a filter. If one reads high pressure in the crankcase and the one that's towards the turbo reads negative draw, then it could be that the filter's plugged up. And if both of them are reading negative draw, then we might have an air filter that's plugged up. So then we have an in the cylinder approach. And the high pressure common rail fuel system by far was one of the best things for diesel as far as lowering the emissions out of the tailpipe. You know, pilot shots, rate shaping the main shot, you know, just the precision of fuel control really did a lot for emissions. But exhaust gas recirculation valves, we have a high pressure EGR system that we've been using for a long time with a cooler. We now have a low pressure EGR that we're using that is filtered, and it's we'll talk about it in a little bit. You might have a manifold that has some sort of active design. It could be trying to create turbulence inside the combustion chamber for a more complete burn. And then the combustion chamber design itself in the bowl of the piston, they can change that parabola effect. They can change the design of that, and it can really do a lot to reduce emissions. Then you have the post-combustion approach, and this is after treatments. When it comes to after treatments, it could be a catalyst, and that's a pass-through device that might be full of precious metals. And what a catalyst is trying to do is either separate molecules or merge molecules. So it's changing the molecule structure. Catalysts are usually full of those really precious metals, kind of like what we're used to with gasoline catalytic converters, palladium, platinum, the unobtainium, the really expensive stuff that they'll put on the substrate material. Then there is a filter. A filter is a catch. So if we say diesel particulate filter, then literally it is something like a vacuum bag that will not let the particulate matter pass. So let's look at the system as a whole. And pardon me if I move this mouse around a lot. I know that can be kind of hard to follow. But if I'm at the air filter right now, this is a design on the Cummins. Then the first thing I'm going through with that pipe up to the turbo inlet is I've got I've got temperature and baro pressure, so atmospheric condition sensor, and then I have a mass airflow sensor. And before EGR systems, diesels really never needed a mass airflow sensor. But if I'm going to introduce exhaust gas to displace clean air, I need to know how much clean air I displaced. So a mass airflow system is in there. Then we come up to the inlet side of the turbo. and that air will be charged, and being so close to the exhaust manifold and the hot wheel of the turbo, and also squeezing, that creates a lot of heat. I'll go through a charge air cooler, will reduce that temperature, and that's important because sometimes right on the other end of the charge air cooler, it might not be a aluminum manifold or a metal manifold. It could be a composite plastic manifold. So after the charge air cooler, I'm going through an intake throttle valve. And this throttle valve is not used for performance. It's used to help the EGR valve flow. So you notice that the EGR valve introduces exhaust gas right after the intake throttle. I want you to picture that you have a lot of acceleration. If you're accelerating and you've got boost air coming through the charge air cooler, and then all of a sudden you reduce acceleration and EGR needs to flow, then you would have surge boost interrupting EGR flow. If they close that intake throttle, they can create a kind of a restriction, and on the intake side, it'll be low enough pressure to let EGR flow uninterrupted. So if I need heat, I got a grid heater, and I'm in the cylinder. So on the intake manifold, you do have a temperature and pressure of the air boost. But once you're in the cylinder and you have a burn, then you're into the exhaust manifold, you've got a pressure sensor, and if you need exhaust gas to lower that 2,500 degree temp, then you can have that exhaust go through an EGR cooler right back into the intake. So this system right here is called the high pressure EGR. High pressure EGR can, some of the codes that we're used to seeing are like insufficient flow codes. So EGR coolers could be plugged up with soot. The crossover tube between the cooler and the valve could be filled up with soot. The EGR valve could be filled up with soot. All that could cause insufficient flow. But it could also be something like a charge air system not delivering enough air, and that could also show up as an insufficient flow code. So EGR system, high pressure. If I'm coming right past the turbo, I've got the after treatments. And if you notice, there's temp sensors between all the after treatments. I've got catalysts and I've got filters. So the dock and the DPF for our vehicles is one canister. There's a temp sensor before the diesel oxidation catalyst, one between mid-bed between the diesel oxidation catalyst and the DPF, and then one that is mid-bed of our selective catalyst reduction. If it's a Cummins, our 3-liter doesn't have that sensor. And then sensor at the end of SCR. You also have a NOx1 and NOx2 sensor. So whatever the EGR did not correct with NOx emissions, it's now an out of the cylinder approach. And what we need to see is reduction between NOx1 and NOx2 to know that this SCR, selective catalyst reduction, is doing what it should be doing, which is reducing NOx emissions. Sometimes the catalyst might need a chemical in order to make it work. In the case of a selective catalyst reduction, there's a chemical reaction that happens when you have 320 degrees of heat go into the SCR. The precious metals are heated up. We can dose synthetic urea and distilled deionized water mixed together in a 67.5 to 32.5% solution. So when it's injected into the exhaust stream, it immediately peels away the water. The aqueous solution will peel away, and what I produce is ammonia. So the ammonia will work with the precious metals, and it will turn NOx emissions into H2O and nitrogen. So coming out of the tailpipe is pretty much atmospheric conditions. Right now you breathed in nitrogen, probably had a little relative humidity on it. Diesel oxidation catalyst, it is something that burns hydrocarbon and carbon monoxide, and what it needs to do is superheat that hydrocarbon carbon monoxide. So when unburnt fuel and partially unburnt fuel hits the precious metals of the dock, it vaporizes. The diesel particulate filters like a big vacuum bag catching all that soot. When it gets to about 65% full, it needs to burn it off. What's interesting is it can use the diesel oxidation catalyst as the heater to get it ready to burn the soot. So if the DPF has a soot trigger, then the PCM will look for speed and temperature, and if the speed and temperature are there, by the way, the temperature it needs is at least 450 degrees at EGT1. If you have 450 degrees right here on the inlet side of the dock, then the way that this vehicle will produce that heat is the PCM will throw fuel into a cylinder 40 degrees after top dead center. It won't help with the burn of the cylinder. It won't help with the power stroke. Basically, the raw fuel's going right through the exhaust stream. It hits that dock, and the diesel oxidation catalyst will vaporize it, and it will superheat, and it will turn 450 degrees into 1112 degrees Fahrenheit, and all that soot will vaporize to ash. So if I had 65% soot, I burn down to 1% ash. 300 miles later, I have 65% soot, it burns down to 2% ash. You're going to get about 300 miles between regen, depending on fuel usage, and then you are going to probably get about 500 regens. Roughly, those are numbers for our vehicles. So about 150,000 miles is a normal wear and tear, and you're plugged up with ash, and you can't get rid of the ash. You have to replace the diesel particulate filter. So some of the things that we've had happen is that customers short trip the vehicle, they don't maintain the highway speed, and it never has a chance to go through the regenerative, active regenerative desoot. So it can't go through that procedure. The PCM's wanting to do it. It might even throw a message on the cluster that says maintain highway speeds. And if the customer shuts it off, then it'll face plug the DPF. And the DPF might have had 499 more regens left. But with that first time, the customer didn't let it do the regen. They didn't maintain highway speeds. It face plugs, and the only solution is to replace the DPF. So we do have some issues that can cause a DPF to fail early, and one of them is customers' driving conditions. Another one is if you had any sort of fuel issue. So if you have raw fuel or air fuel mixtures that produce a lot of soot, instead of 300 miles between regen, let's say you only get 50 miles between regen. So now those 500 regens that you were supposed to get, you're not going to get them in 150K. You're going to get them in like 35,000 miles. So the diesel oxidation catalyst, if I can never get that temperature on the inlet side of the dock, it could be that the VGT is not working correctly to create that heat by creating back pressure releasing, back pressure releasing. It could be that you never got the pre-temp. It could be that it gets the pre-temp, but the diesel oxidation catalyst precious metals aren't working correctly enough to create the heat needed to burn off the soot. So some of the things to look at are temperatures, and I'm just going to tell them to you. You know, they might be a little different from one manufacturer to the next, but if this is going through a regen, 450 degrees will get turned into 1,112 degrees, and I can't start dosing urea, synthetic urea DEF fluid, until I have about 320 degrees. If I was to put the synthetic urea distilled deionized diesel emission fluid into the exhaust stream and I don't have enough heat, it will just crystallize, and they call it snowballing the tip. So I'm telling you, the temperatures are very important. Closed crankcase ventilation. You've got a CCV filter, and on this system right here, closed crankcase ventilation filter, you have a pressure sensor for the crankcase and then you have a pressure sensor that's going towards the turbo. We call this the line disconnect because it goes towards the inlet side of the turbo. So we'll just call them crankcase 1 and crankcase 2. In between it is a filter. If they read the same, it could be that the filter is not there. If one reads really high crankcase pressure and one reads negative draw, it could be that the filter's plugging up. If I had a negative draw from the turbo and I had a little bit of a negative draw on the crankcase, it could be that the air filter is so plugged up, the regular air filter, that the engine is trying to breathe through the crankcase. In the event of that, we do have a big check valve on this, big rubber diaphragm that it will check the engine from drawing too much pressure from the crankcase. Let's see. So EGR systems. So exhaust gas recirculation systems. I want to call these guys either high pressure or low pressure. The high pressure are the traditional ones. You know, exhaust gas recirculation on diesels is really different than what I'm used to on gasoline. You know, gasoline EGR, I'm used to only seeing the valve really on cruising speed conditions. Exhaust gas on diesels is you see them wide open EGR during idle. So at idle, EGR is flowing. When you have high calculated engine load, then the EGR starts to close up. So the more throttle, the more EGR closes. The more you come off the throttle and it's idling, the more EGR flows. You have that mixture of anywhere from 145 to 1, that would be your idle, to 20 to 1, that would be your hammering down on the throttle. So an EGR valve has a lot of feedback to see if it's opening. It's got a stepper motor in there. It might have one plunger or it might have two plungers. It has a linear potentiometer to where it knows the stepper position. And then it has a temp sensor on the crossover. So the temp sensor on a crossover tube will let you know that exhaust gas is flowing on the tube. So those are two feedbacks. There's also back pressure of exhaust. So if you introduce exhaust gas into the intake, then it lowers the pressure on the exhaust manifold. You also have the boost sensor. So the boost pressure on the intake manifold, it will change due to EGR flow. Last is the mass airflow. The mass airflow sensor near the air filter housing will say that clean air was displaced. EGR flow can even be a PCM function to manage oxygen content. If you have a really hot combustion chamber at 2,500 degrees, if you put an inert gas in there, you can lower the oxygen content and that will lower the temperature of the combustion chamber. But it doesn't stop, you know, the engine completely, and you still have power. You're just trying to lower that temperature a little bit. Let's see. So high pressure EGR. High pressure EGR systems have a cooler, and I'll be honest with you, they're bad about collecting soot. There's also a low pressure EGR system that we're using on our 3-liter Vancini Martelli engine. We put that in the 1500 in the JL Jeep Wrangler platforms, Gladiator. So the low pressure EGR is the tube for the EGR flow is in between the DPF and the SCR. So the diesel particulate filter collected all the soot. That means that EGR flow is clean. It's coming with no black soot. Goes through a cooler and it's being introduced at the inlet side of the turbo. So you can have insufficient flow codes on this, kind of like you've had on the high pressure side. You do have a valve. The valve itself is real close to the end of its, right before the inlet side of the turbo. And then you have a butterfly in the exhaust that is a way to create back pressure in the exhaust so EGR can flow. This EGR system can be used cruising speeds at low RPM. So when you get that desired temperature, the engine's up to operating temperature, low pressure EGR is a way to kind of get clean exhaust gas to lower combustion chamber temperature, rather than the high pressure system, which has soot. For that butterfly, if you've ever seen exhaust valves be a failure on vehicles before, just know that that's clean. It's not like on gasoline vehicles where a lot of times it was a lot of sulfur in the content in the fuel would cause them to rust up and become an issue. So let's see. The low pressure EGR exhaust control valve, it defaults wide open. So the default spring load on this thing is that it would not restrict flow. So if electrically you disconnect it, the butterfly would be in a wide open position. So how do you diagnose an EGR system? I would start off with know all your normal feedback sensor values, key on, engine off, and key on, engine running. Look at the linear potentiometers, maybe do a throttle valve, an EGR valve actuation. So you can look at the actuation of those valves, make sure that not only are they being commanded, but they're physically moving. The EGR crossover tube temperature, if you cold soak it and let it sit for a long time, that temp should be about the same as ambient air temp. If you start the vehicle up at idle, EGR will flow, and you should see that temperature rise with your first exhaust gas temp sensor. They should be about the same. So EGR flow is highest at idle and least at high engine load. Mass airflow, a lot of times your manufacturer will have specifications for at idle, at 1500, at 2500 RPM, what should mass airflow read? I would know what normal is. If you're ever trying to diagnose looking at a scan tool, if you don't know what normal values are, that can beat you up a little bit. Sometimes you might not get a code. One thing that I've always worried about EGR systems is if they stick open. We test really hard to see if they're flowing, but to see if they're shutting off, we might not be testing, it might be something that you have to test in alternate methods. One quick test I've seen for EGR for diesels is if you feel like it's stuck open, disconnect the EGR valve itself. That would command it, with no electricity on the EGR valve, it is closed. On a cold soaked engine, if you put your hand on the crossover tube and you were to start the vehicle up, if the EGR valve is closed, that tube should stay cool. But if it was to immediately start to gain temperature, you know that the EGR valve is stuck open. So low flow, insufficient flow codes on EGR, know that it's probably going to be checking the air filter, checking the air for restrictions and leaks. It's real common with underboost. As a matter of fact, if you had both an underboost code and an EGR insufficient flow code, they really share that in common, the charge air side of the system. You could have a clamp loose, you could have a hose with a tear, you could have a charge air cooler leaking or an intake manifold leaking. All of those things could be an issue with both EGR and underboost. Check for leaks. EGR systems got clamps and coolers and valves. If you see black soot under hood, that could cause an issue. One of the things that you could do if you're kind of stumped and there's not much more to do, check that crossover tube. The crossover tube goes between the cooler and the EGR valve, and if it is chock full of soot, that's the reason why you got the low flow. It might have a service interval in there to where a cleaning procedure is recommended. We've actually, some manufacturers might have that maintenance interval. But usually somewhere right around 70,000 miles, you know, it wouldn't be abnormal for those to start to show heavy soot accumulation. Now, chalky dust, that's normal. If I saw sticky dust to where it was gummy, that means you have an EGR cooler that most likely is cracked, and the coolant is getting into the exhaust flow. On a Cummins that has 70 psi back pressure capability, you might even have exhaust getting into the coolant with pressures high enough to cause coolant damage, like a ruptured hose. So if you were to step on the brakes and create 70% of 70 psi back pressure, it could swell out your coolant hoses. So another thing is I've seen where people do head gasket combustible gas leak checkers into the coolant, squeeze ball, the blue dye turns green kind of thing. If you ever see that on a diesel, I want you to think cooler first. Don't think head gasket first. Think EGR cooler. Then, you know, if it is gummy, replace. The cooler needs to be replaced. So you could remove the cooler if it's chalky dust. You could remove the crossover tube and the EGR valve minus the electronics of the valve and dip it into an aqueous solution. We've got a 4-to-1 water to EGR cleaner solution, and you could clean it. I think what I've seen most of our technicians do is they get turkey cookers, stainless steel pot with propane on the bottom, and they agitate the fluid, and when it's boiling, they clean the EGR components. I also have seen where there's some misting services there. Probably removal and cleaning would be your best bet to not see that vehicle back for a long time. Insufficient flow due to chalky normal dust and soot. Just real quick on the powertrain control module, talking about some of the emission systems. Throttle valve actuation works in tandem with EGR. This is, if I want EGR flow, I'm probably going to have to get rid of some of that potential surge boost, or at least create a low pressure on the other side of that throttle valve to let EGR flow. The crankcase, if I'm allowing crankcase to go into the inlet side of the turbo, you have seen on cold days where you can get ice chips and condensation. That tube right there, we have a little 2-wire heater to prevent that. We have a cooler bypass system. If you have a cooler bypass system, there are times to where you do not want to go through the EGR cooler. If you're doing a regen, raw fuels being put into the exhaust stream 40 degrees after top dead center, we're using it as post-injection with regular diesel injectors. We wouldn't want it at that point to go through the cooler because it would be like spraying WD-40 and throwing soot. It's definitely going to stick. So there are times to where we try to bypass the cooler. Let's see, moving on to, let's see, urea injector, PCM controlled, that's your DEF injector. You have level quantity pumps, heaters for the urea, for the DEF fluid, the reductant. That right there for the 3-liter VM diesel, that's all PCM controlled. I don't know if we said this earlier, but when it came to the diesel oxidation catalyst, the diesel particulate filter, and the SCR, we talked about the temp sensors. If you ever have an issue with any one of those, cold soak the engine, make sure that all your exhaust gas temps are plus or minus 5 degrees of each other. All right. So soot, it's normal. You know, black chalky soot is not an abnormal thing. Now, if you got really heavy accumulated soot, and it could be that you have something like an overfueling condition, or you have a lack of charge air. If you have a lack of charge air, you'll be running rich. So a fuel issue would cause heavy soot accumulation. And if you get to the tail end of life of a diesel particulate filter, the regens start to get shorter and shorter and shorter. The soot accumulation can get worse. So after treatments, you've got the DOC, the DPF, and SCR. In between the diesel particulate filter is a delta sensor. The delta pressure sensor is a tube on the inlet side of the DPF and a tube on the outlet side of the DPF. This is how they find out how much soot is accumulated across the DPF. We've had a lot of weird things with the delta sensor to where potentially you could get water in one of the rubber hoses or one of the tubes. People have put the hoses on backwards. If you forget to put a hose on, you could make it to where the DPF never get the trigger. So it's never going to run a regen because it never has the, never sees the soot accumulation. So when after treatment, scan tool data is I want you to know what is normal. Key on, engine off, do a rationale of your sensors. All the exhaust gas temps should be plus or minus, I put 10 degrees, but plus or minus 5 degrees or so of each other. The diesel particulate filter delta pressure sensor. I should never see that thing in a negative number. A negative number on delta pressure would mean that the downstream is higher pressure than the upstream. When I really heavily throttle this thing, 2,800 RPM, I should see, even if the DPF is not plugged, I should see some pressure differential between the upstream and the downstream. Some delta pressure positive difference. Boost, baro, exhaust pressure, need to rationale all those. Make sure that baro, rationale amongst a vehicle right beside it. Does it show barometric pressure? Boost and exhaust pressure, you can rationale those two amongst themselves. Know what normal key on engine running. If you're running this vehicle, my exhaust gas temps will start to warm up, and during a regen, if you got 450 to 600 on the inlet side of the dock, you should be able to create 1112 degrees on the outlet side of the dock. If you have the inlet and you don't have the outlet, the dock's not doing it. If you don't get the inlet, the variable geometry turbo is not creating the heat. That throttle control valve that's used with the EGR system can also be used to create heat. 320 degrees, you need to have that in order to start dosing at the SCR catalyst. So that's a temperature to kind of keep mind of. And then the differential pressure rationale, we talked about it a little bit. NOx 1 and NOx 2, those are very smart sensors. They're usually, for us, they're on a private communication network with PCM. So NOx 1 and NOx 2, what I should see is reduction. So if I'm not dosing DEF, NOx 1 and NOx 2 should be the same. If I am dosing DEF, then I should see reduction between NOx 1 and NOx 2. And if I feel like NOx 1 is not moving, I'll disconnect the EGR and I should see NOx 1 climb rapidly. And then I'll replug back into EGR. So rationale, NOx 1 and NOx 2, make sure that they're working correctly. In order for a DPF to do a regen, you got to have the soot trigger. That delta pressure sensor's got to see 65 degrees or 65% of full. Then you also have to have the temp and the speed. You got to have the 450 degrees. You got to have speed because they don't want to melt the fascia of the vehicle and the traffic jam beside you. So speed is important to get a little ram airflow. And you can't have any trouble codes. You can't be low on fuel. So normal life is 300 miles between regen. As it starts to get to an end of its life, it'll start to get lower and lower miles between regens. High fuel usage and city driving, all those things can cause a reduction of that 150K. Diesel oxidation catalyst issues can cause a face plug DPF because it never reached temp. Inlet and outlet temps are pretty important for you to diagnose a DOC. If efficient, the inlet temp never achieved could be due to a turbo or an exhaust leak or throttle control valve. And if the inlet temp is achieved at 450, but the dock is not doing with high hydrocarbon post-injection or hydrocarbon dosing, then the DOC is your problem. So the DOC needs to be able to raise temperature. The DPF, customer driving characteristics, aftermarket software, fuel issues, air issues, EGR issues, oil ingestion due to a turbo seal or blow-by, all of those things can cause the DPF to go early. As a matter of fact, the nickname of the DPF is the diesel fuse because it usually tells that something else is going on. If you have a fuel issue, DPF plugs up quick. If you have an air issue, same thing. So replacement is not the fix. If you have a DPF that's plugged up, replacing the DPF is not going to fix your problem. It's only going to fix the effect, and the root cause is just going to cause that very expensive DPF to have to be replaced again. So anytime you have a DPF replacement, you really, especially if it seems early, you have to find out what the problem is. Start with aftermarket software, then move on to fuel, then air, then EGR, then oil ingestion. You'll probably find the problem. A little bit about this pump. So I've got a DEF tank that if I have a pump or a two-pump system, I have heaters, and there is a quick test on this line. If the injector is closed and I'm getting ready to start dosing, the pump will energize. I'll hold pressure, and can the system hold pressure? So that is a prime test. Can the pump build and hold pressure? Then they'll shoot one shot. Does it release pressure? So all of those are tests just to make sure that the pump, that the line's not leaking, that the pump can build the pressure, and that the injector can hold the pressure, and that once the injector is opened, that stream of DEF fluid will release pressure on the line. So that's a pretty quick test, and if you ever have any failure of that test, just know that you're usually looking for leaks on the line. You might have to remove this injector and put it into a bucket and run a pump test. The pump test is, we nickname it the bucket test. Do you get the right amount of volume with a 6-minute test? If the volume is low, if the volume is high, that could be an issue why you have cat efficiency issues. The SCR catalyst, the cat efficiency issue on this could be due to DEF fluid not being the right concentration. It could be contaminated. It could be not being pumped. It could be leaking. It could be that the dosing valve is not allowing it to get into the exhaust stream, or it could be the precious metals. You have to separate. The bucket test will tell you most of it right then and there, because you can sample the volume of fluid that you collected in your volumetric cylinder. So if you test that fluid, you can test it with a refractometer, with a pH stick, with hydrocarbon test strips. But bottom line is, if I ever have a cat efficiency code on an SCR, I'm probably going to dump the DEF fluid, put new DEF fluid, put about 40 miles on it, and see if that fixes it. So you can fluid, look for refractometer to show the horizon line. Anytime you try to fix it with new DEF fluid because you smelled ammonia heavy in the fluid, or you saw that the concentration wasn't correct, or you saw where it looked like it was contaminated, so you put new fluid in it. Don't forget, you got to put some miles on it to see if it's going to work correctly. I like to call that the SCR healing procedure. It's about 50 miles. DEF tank empty issues. If you have dash messages, those are usually kind of hard to get rid of. So some of those instrument panel cluster messages, even if you fill it up with DEF fluid, they might be hard to clear. So, if they do go DEF tank empty, we have onboard diagnostic too. Some of the mandates are pretty heavy. They can derate, and they can create a no start condition. SCR plugging. If a DEF injector is putting out too much fluid, it can snowball the tip. If the DEF injector is not if the DEF is not a good solution, it can snowball the tip. And if you're not up to temperature, it can snowball the tip. So a lot of times, if you have just caked this thing with ammonia and it's been sitting on there, it might do damage to the SCR itself. So engine mechanical, this is only one slide, just real quick, just a refresher. And if you do have engine mechanical issues, we do have a couple programs on Scan Tools, different, one's called System Run-Up Test, and that's on the Cummins. That will high rev it and do an injector kill on number one. It will do every cylinder 3 times. So it is a kind of a power contribution test. Then it will also show us the amount of fuel correction. A diesel engine, I can trim every cylinder. If every other revolution, number one is slow, then I can plus up the fuel on number one. So I can trim number one injector to keep the engine balanced. Well, that system run-up test will show you the amount of fuel correction. So if I see a real heavy number for fuel correction, that could be due to a bad injector, or it could be due to a loss of compression. One way that you can find out if it's a loss of compression is a compression test. Engine compression test would require the removal of every injector. That is a very tedious process. But you could put an amp clamp on the battery negative, disable fuel, and with a lab scope, look at the amperage pulses that the starter is going to have as amperage draw. If I saw 5 of the 6 cylinders with high spikes in amperage, but one of the cylinders shows a low spike in starter amperage, that could be due to a compression issue. If you don't see a relative compression issue, sometimes on some vehicles, if they let you replace the high pressure, or they make it to where you can reuse the high pressure line, multiple use high pressure line, you could try and inject, see if it follows the injector. If it follows the injector, then you can replace that injector and transfer tube. Okay, if you had noises, like any sort of engine noise, probably just make sure it's not an accessory. If you remove the accessory belt for a second, start it up, and for a short term to see if the noise goes away. If the noise is still there, put the belt back on. If it's an RPM related noise and you kill one injector and the noise goes away, you got rid of the power stroke for that cylinder. It could be a rod knock. All these high pressure fuel pumps, there is a way that if you get lucky and roll the dice, you might make it to where it harmonizes with the firing pulses of the engine. And if you get that, that will cause a noise that can sound metallic. So we require that we phase the fuel pumps. It's not so much timing them for operations. The fuel pump would work in any cogged position. The problem is noises. So for NVH, noise, vibration, harshness, we phase it in order to offset the harmony with the firing pulses of the engine. So valve train noises, it might get to the point where you have to take the cylinder head cover off and look at the valve springs and rocker assemblies and just see if you've got some sort of noise up on the top end of it. If you have an all cylinders are you're feeling like it's all cylinders are weak, you might have an issue to where crankcase pressure testing might be so much blow by that if you remove the oil fill cap, it's a choo-choo train. So you could check for crankcase pressure. What's cool about diesels with closed crankcase ventilation is you have a pressure sensor. If you know what normal is, you might see abnormally high pressure, crankcase pressure on those sensors. So we've been here talking for a long time, and I really appreciate all that you guys do in the shop, and I know it's not an easy job, but I hope that this was helpful for you. I hope that there's something that you could have drawn from it. And I'm going to open it up to any questions.
Thank you, Matt. Really appreciate it. A lot of good information, a lot of comments from the audience talking about the quality of the content and things that they learned. So very much appreciated there. I know it's a long session. We've kind of crammed it in, and as a result of that, we're only going to be able to take about 2 questions from the audience this evening. So with that, I just want to remind everybody that your certificate of attendance comes by email automatically to the name that you put on it, the email address that you entered. That's where it will go. We have no control over it. We don't touch any of that information. So if there was an error in any of that, there's going to be an error in getting the certificate out to you. So I just want to mention that. Again, a reminder, there will be no session next week. So everybody be aware of that. And with that, Dan, what do you got?
Matt, David and James had a question related to the CP4 failures. Is there a specific cause to look for or a common reason why those CP4 pumps are failing?
You know, that's a great question, and I know that CP4 has got a history that predates being used on the Cummins and in our vehicles. I know the CP4 is a very common pump, but I would say fuel quality above all things. You know, there's even a question of fuel quality, gasoline intrusion, water intrusion, and then any particulates. It was something that's squeezing up to 29,000 PSI. One little piece of trash, it just creates havoc. The change that we're making on the model year 2019 is a change in the lobe. So the profile of the lobe on our revised pump is going to be a little bit softer than the aggressive lobe that was on the earlier version of the CP4. So I mean, we just had a little training session on not too long ago, and they showed a picture of the lobe profile, and it was dramatically different. So we're getting ready to change some pumps out, but we're going to stick to that design. You know, it's a strong pump. It's a light, it's strong pump, but fuel quality, that would always be my first suspect. Is that you know, it got some trash in the system somewhere.
Okay, and then from Earl, they've got a fleet application, and they're curious about the snowballing of the tip because that seems to be a widespread issue for them. Are there any methods that can be performed to prevent that from happening?
DEF fluid that's a great question because I've seen that a lot. And the DEF fluid has to be this mixture of synthetic urea to distilled deionized water. In the storage of DEF fluid, if there's any heat, you know, if you're above 75 degrees and you store DEF fluid, it really starts to turn pretty fast. And I can smell it. The moment I open up the container, if I smell heavy ammonia, then it's already turned. It's already bad. And the way that the PCM manages the dosing of the diesel emission fluid is that it's looking for reduction, and it trims it down, and every once in a while it kind of lifts up on the pulse width, and then it increases again, and it's really wanting to monitor reduction on NOx2. But if that fluid is not doing it because the concentration is not correct, or it's already started to turn south, even though you got a good fluid, it might be being stored in a big drum in the outside elements. Then what's happening is the PCM's desperately trying to get reduction, and it's overdosing to try to get the reduction. So there's really not much more to peel it back on the volume side. It could be that the fleet, vehicles don't have a quality sensor. What we see on the non-commercial side a lot of times is that the PCM sees that you just filled fluid. They see a recent key cycle and the fluid level changed on the DEF tank. And then they notice that NOx1 and NOx2 don't show reduction. So we can almost immediately say it's a quality issue. But if it turns south on the vehicle, like we have vehicles that are on the new car lots that they're full of DEF fluid in the middle of summer, and they're slowly starting to have the fluid go bad in the tank, then it can overdose to try to get reduction, especially if it's a slow degradation of the fluid.
Matt, the chat pane was blown up with thank yous for a great presentation. Also, you've had a lot of, there's been a lot of input, folks looking for more detail. They really need to seek some more training or to find that detail. So I'm going to pass this over to Dave. Thank you very much, Matt, for your presentation. And again, the chat pane and the questions pane are blowing up with thank you. So well done.
Yeah, thank you. Thanks, everybody. I hope you have a great weekend, great holiday.
Yeah, and I'll echo what Dan said. Thank you very much, Matt. Great job. Thanks to Matt Rieger from FCA for today's presentation on light-duty diesel technology. Without a doubt, modern diesel technology has come a long way from diesels with mechanical fuel systems. This webcast was brought to you by ASE and the ASE Education Foundation. For announcements about upcoming sessions, watch your email inbox. On behalf of Matt Rieger, Kelly Tran, and Dan Baumhart, I'm Dave Kappert, and this concludes today's webcast. We hope to see you online at another event soon. Have a good weekend, everyone.